if we focus on trend non-stationarity first, then we can say that a time series exhibits a trend if it has a persistent long-term movement. And we differed between two types of trends. One is deterministic and the other is stochastic. And the deterministic trend is, you can think of it as, for example, money in the bank. Okay, if you have locked in your money for 10 years, then you will get the same interest rate for all those years. So then you have this slightly upward deterministic trend, right? Because if you are here at time equals 0 and you would like to know what is the value of my money at year 5, then you would know quite certain with a great deal of certainty what is the amount of money in your bank account. So this is a picture of the deterministic trend. Another example can be that the GDP growth rate increases by 0.75 percentage points per quarter, and you just write the trend as 0.75 times t. So here they have assumed a linear trend. Here you have the exponential deterministic trend because you get compound interest. But this is the linear trend is often a simplification, or it can be that GDP is measured in logarithms, which means that the exponential trend is actually a linear trend in the logarithmic plane. This is the idea behind the deterministic trend. You know exactly where the trend is going. And the stochastic trend is a random function of time. So you can think about, for example, GDP. If we say that, well, it's not deterministic, it's more a stochastic trend, and that would, for example, portray itself as strong growth for 10 years, and then low growth for 5 years, and then strong growth again, for example. It's not a deterministic trend, but it's trending kind of. The trend is changing. Okay, so you can say that this is a strong trend, this is a weak trend, and this is a strong trend again. But the question is, why do we care about these trends? And actually, many economic time series, they are portrayals of trends. So, for example, if you look at the GDP or inflation or currency rates, they are often modeled using stochastic trends. It's not very common to have deterministic trends in economics because the world is always changing. So it's quite unbelievable to be able to forecast economic time series with the grade of certainty that a deterministic trend actually portrays itself as. So we usually focus on stochastic trends and use this to explain economic time series. A quite important problem with stochastic trends is that it gives us problems with the regression estimation. So for example, if you have an autoregressive model on the y variable, yt equals, for example, the beta naught, the intercept, plus beta 1, yt minus 1, plus the error term at time t, then if the y variable actually has a stochastic trend, maybe you are modeling this or using this model to explain the stock price, and then you would have a problem with a bias in the slope here, and the slope would probably be biased towards 0, and the bias here can be quite substantial if the sample size is small. And this bias, even though it might be a small bias, it might skew your forecast of the next period value. And this bias might even be such that the forecast of your model is worse than a pure random walk model. And the pure random walk model is this AR1 model with beta equal to 1. And we're going to just discuss this more in detail in a later video in section 4.2.1. And another problem is that the distribution of the t-statistics might be non-normal. Remember that when we test the coefficient on a variable, then we use that the sample distribution is t-distributed, right? Or almost normally distributed. So and this t-distribution, it approaches the normal distribution as we get more data. And we saw that in the previous slide, we saw that this distribution might be biased, and which means that this is the distribution of the beta hat, but the true beta might be here, and it might also be non-normal, which means that it might be skewed, which means that it has a fatter tail at one end, or you might have problems with kurtosis, which means that both tails might be too fat, for example. So this means that we can't trust the t-statistics, which is our coefficient divided by the standard error of the coefficient, and this will not give us a useful number to compare to any critical values. And the third problem might be spurious regression, and this happens if you have two time series and they are actually independent. Okay, so they are not causing each other, and but they have stochastic trends, and sometimes two independent and unrelated time series, they might appear to be related because they just happen to have coincidental stochastic trends. And the following figure can actually give us a kind of a picture of such a stochastic or spurious relationship, because here you have the red graph is the US crude oil imports from Norway, and we see that, well, it went up until 2002 and then sharply down until 2004 and then moderately down until 2009. And coincidentally, this pattern of trend, the stochastic trend, happened to drivers killed in collision with railway train. And you would not believe that there is any causal or long-term kind of relationship between these two time series. So we are drawing the conclusion that this correlation may be spurious.